Hello everyone and welcome to this video on Apache Spark. In this video, we will understand what Apache Spark is, why it was created, and how it works internally. We'll then explore about RDDs, the fundamental data abstraction in Spark that enables fault tolerance and distributed computation. From there, we'll move on to data frames and datasets, which provide a higher level, more optimized and easier to use API for structured and semi-structured data processing. We'll also understand how Spark internally processes application using directed acyclic graph. Next, we'll explain how Spark execution work using jobs, stage, and tasks. We'll then take a look at Spark core components and libraries. Finally, we'll wrap up by discussing the advantages and limitations of Apache Spark. By the end of this video, you will have a clear and practical understanding of Apache Spark and how it's used to solve real-world big data problems. Let's begin with an introduction to Apache Spark. Apache Spark is an open-source, distributed data processing framework designed to process large volumes of data quickly and efficiently. It was originally developed at the University of California, Berkeley, and later became an Apache open source project. Today, Apache Spark is widely used across industries for big data processing, analytics, and machine learning. One of the key reasons Spark is so powerful is its ability to perform in-memory processing. Unlike traditional systems that read and write data to disk at every step, Spark keeps data in memory whenever possible, significantly improving performance. Spark also supports multiple programming languages such as Scala, Python, Java, and R, making it accessible to a wide range of developers and data engineers. Apache Spark is not limited to batch processing. It supports multiple types of workloads, including batch processing, real-time streaming, interactive queries, machine learning, and graph processing, all within a single unified engine. Because of its speed, scalability, and flexibility, Apache Spark has become a core component of modern-day platform and is widely adopted by organizations to process and analyze large-scale data efficiently. Apache Spark can run in different deployment modes depending on the environment and use case. It is local mode, standalone mode, yarn, and mesos. Now that we have introduced Apache Spark, let's understand why Apache Spark was needed in the first place. Before Spark, Hadoop MapReduce was the most widely used framework for big data processing. MapReduce was reliable and scalable. It had one major limitation. It was slow for many types of workloads. MapReduce processed data by reading from disk and writing back to disk at every step. This disk-based processing creates a lot of input and output overhead, making it inefficient for interactive algorithms, interactive queries, and real-time analytics. As data volume grew and business requirements evolved, organizations needed a faster and more flexible processing engine that could handle different type of workloads, not just batch jobs. This is where Apache Spark come in. Apache Spark was designed to perform in-memory processing, which means it keeps data in memory whenever possible, instead of constantly writing it to disk. This dramatically reduces execution time and improves performance. Spark is especially well suited for workloads like machine learning, data analytics, and streaming, where the same data needs to be processed multiple times. Another important reason for Spark adoption is its unified platform. Unlike older systems that require separate tools for batch processing, streaming, machine learning, and graph processing, Spark provides all of these capabilities within a single engine. In summary, Apache Spark was created to overcome the performance limitation of disk-based processing system, support modern real-time and interactive workloads, and provide unified high-speed engine for big data processing. Now let's understand architecture of Apache Spark. At a high level, a Spark application runs on a distributed cluster and consists of three main components: the driver program, the cluster manager, and multiple executors. The driver program is the central coordinator of a Spark application. It runs the main application logic, creates the execution plan, and manages communication with the cluster. Inside the driver program, an important component is the Spark context. The Spark context is the entry point Spark's core functionality. It represents the connection between your Spark application and the cluster. When your application starts, the Spark context contacts the cluster manager to request resources such as CPU, cores, and memory. It also keeps track of executors, schedule tasks, and manages metadata about RDD. When you submit a Spark job, the driver converts your code into a logical execution graph known as a directed acyclic graph or DAG. The DAG represents a sequence of transformations that needed to be applied to the data. The cluster manager is responsible for allocating cluster resources. Spark can work with different cluster managers such as standalone, Yarn, Mesos, and Kubernetes. The cluster manager launches executor process on worker nodes and assign CPU cores and memory to each Spark application. The executor are a worker process that runs on the cluster nodes. They execute tasks, process data in parallel, and store data in memory or disk as required. Each executor runs multiple tasks simultaneously and sends result back to the driver program. Data in Spark is divided into smaller units called partition. Each partition is processed independently by a task, enabling parallel execution across the cluster. Spark's architecture also includes key internal components such as the DAG scheduler, task scheduler, and block manager. The DAG scheduler breaks the DAG into stages based on shuffle boundaries. The task scheduler then assigns tasks to each executor for execution. The block manager handles storage and retrieval of data blocks, enabling in-memory caching and efficient data sharing between executors. Now let's understand one of the most important concepts in Apache Spark, the resilient distributed dataset, commonly known as an RDD. RDD is the fundamental data structure of Apache Spark. It represents a distributed collection of data that can be processed in parallel across multiple nodes in a cluster. The term resilient means that data are fault tolerant. If a part of the data is lost due to a node failure, Spark can automatically be computed using the lineage information. The word distributed indicates that the data is divided into smaller partitions and spread across different machines in the cluster, allowing parallel processing. And finally, dataset simply means a collection of data elements. RDDs are immutable, which means once created, they cannot be changed. Instead of modifying an existing RDD, Spark creates a new RDD when you apply transformations. RDD are created in two main ways. First, by loading data from an external source such as HDFS, S3, or a local file system. Second, by transforming an existing RDD using operations like map, filter, or reduce. RDD operations are broadly classified in two types: transformations and actions. Transformations such as map, filter, and flat map defines how the data should be processed, but they do not immediately execute. They are lazily evaluated. Actions such as collect, count, or save trigger the actual execution and return result to the driver or write output to the storage. Another powerful feature of RDD is lineage. Spark keeps track of all the transformations used to build an RDD, which allow it to recompute lost data automatically without relying on data replication. RDD can also be cached in memory, making repeated access to the same data extremely fast, which is especially useful in iterative algorithms and machine learning workloads. Now let's move on to two powerful and widely used abstraction in Apache Spark, DataFrame and Datasets. While RDD provide low-level control, DataFrame and Datasets offer a higher level and more optimized way to work with structured data and semi-structured data. A data frame is a distributed collection of data organized into named columns similar to table in a relational database or a spreadsheet. It allows you to work with data using SQL-like operations such as select, filter, group by, and join, making data processing more intuitive and expressive. Unlike RDD, data frames are schema-aware, meaning Spark understands the structure of the data, the column names, and data types. This enables Spark to apply powerful optimization through the Catalyst Optimizer and execute queries using the Tungsten execution engine. Data frames are also language agnostic and are available in multiple APIs such as Python, Scala, Java, and R. Now let's talk about datasets. A dataset is a strongly typed collection of objects that combine the benefit of RDD and data frames. Like DataFrame, datasets are optimized and support high-level operations. And like R2D, they provide type safety and object-oriented programming, especially when using Scala or Java. Datasets are primarily used in Scala and Java. In Python, PySpark mainly works with DataFrames. Both DataFrame and datasets are evaluated visually, means Spark does not execute operations immediately. Instead, it builds an execution plan and runs it only when an action is triggered. They also support in-memory caching and efficient serialization, making them extremely fast for large-scale analytics and machine learning workloads. Now let's understand the concept of directed acyclic graph, commonly known as DAG, in Apache Spark. A DAG is a logical representation of all the operations that Spark needs to perform on a dataset. The term directed means that each step has a specific direction of execution. Acyclic means there are no loops. The data flow forward from one operation to next without returning back. Whenever you write a Spark program using transformation like map, filter, or join, Spark does not immediately execute them. Instead, it builds a DAG that represents the sequence of these operations. This is possible because the Spark follow a concept called lazy evaluation. Spark wait until an action such as collect, count, or save is triggered before executing the transformations. Once an action is triggered, Spark analyzes the DAG and optimizes the execution plan using the Catalyst Optimizer. The DAG is then divided into smaller units called stages based on operations that require data shuffling. Each stage is further broken down into tasks which are executed in parallel across the cluster. If a task fails, Spark does not restart the entire job. Instead, it only recomputes the missing part of the DAG, making the system highly fault tolerant. Now let's understand how Spark's breakdown work internally using jobs, stages, and tasks. These three concepts define how a Spark application is executed on a cluster. A job is created whenever action is called in a Spark application, such as collect, count, or save. Each action triggered a new job. So if your application contains multiple actions, Spark will create multiple jobs. Once a job is created, Spark analyzes the execution plan and divides the job into smaller units called stages. Stage represents a set of operations that can be executed together without requiring data to be reshuffled. Stage boundaries are formed whenever Spark encounters a transformation that requires data shuffling, such as load by, reduce by key, or join. This means all the tasks in the current stage must complete before the next stage can begin. Assume there are three transformations happening on a dataset: map, filter, and reduce by key. Then map and filter needs to be executed in one stage and reduce by key should execute in later stage. Each stage is then further divided into tasks. A task is the smallest unit of execution part and represents the work performed on a single data partition. Each task is executed by an executor on a worker node, processing a portion of the dataset in parallel. The number of tasks in a stage typically depends on the number of partitions in the data. Spark runs many tasks simultaneously across the cluster, enabling high-performance parallel processing. If a task fails due to a node failure or error, Spark can retry that task on another executor using the same image information. Now let's explore the key components and libraries of Apache Spark that make it a powerful and versatile data processing framework. At the core of the Spark is the Spark Core Engine. Spark Core provides the fundamental functionality of Spark, including task scheduling, memory management, fault recovery, and interaction with storage systems like HDFS, S3, and local file system. It also contains the API for creating R2D and perform basic operations. Built on top of Spark Core are several specialized libraries that extend Spark capabilities for different use cases. The first major library is the Spark SQL. Spark SQL allows you to work with structured data using SQL queries, data frames, and datasets. It enables seamless integration between SQL and Spark program and support querying data from sources like Hive, JSON, PyK, and JDBC database. Next is Spark Streaming, which enables real-time data processing. Spark Streaming allows Spark to process live data streams from sources such as Kafka, Flume, and Socket, making it suitable for applications like real-time analytics, fraud detection, and monitoring systems. Another powerful library is MLib, Spark Machine Learning Library. MLib provides scalable implementation of common machine learning algorithms, including classification, regression, clustering, recommendation systems, all optimized for distributed environments. Then we have GraphX, which is used for graph processing and graph analytics. GraphX allow you to work with graph structure data and perform operations like PageRank, connected component, and network analysis. Together, these libraries allow Spark to support batch processing, streaming, machine learning, and graph computation, all within a single unified platform. Now let's take a look at the advantage and disadvantage of Apache Spark to understand where Spark excels and where it has limitations. Let's start with the advantages. One of the biggest strengths of Apache Spark is its high performance. Spark processes data in memory, which make it significantly faster than traditional disk-based systems like MapReduce. Spark provides high-level API in multiple languages such as Python, Scala, Java, and R, making it accessible to a wide range of developers. Spark is also extremely versatile, with built-in support for batch processing, streaming, machine learning, and graph processing. Spark can handle multiple workloads using a single unified platform. Spark offers excellent scalability and fault tolerance. It can process data across thousands of nodes and automatically recover from failure using lineage information. Additionally, Spark integrates easily with powerful storage systems like HDFS, S3, Hive, and many databases, making it highly flexible in real-time environments. Now let's look at the limitation of Apache Spark. One limitation is that Spark requires large memory resources. Since Spark relies heavily on in-memory computation, it can become expensive in environments with limited RAM. Another challenge is complex tuning and configuration. Optimizing Spark for performance often requires careful configuration of memory, partition, cluster resources. Finally, debugging in a Spark application can be more difficult compared to traditional single-node programs, especially when dealing with large clusters. Apache Spark is not just a big data tool. It's a powerful engine driving real-time analytics and intelligent data processing. Mastering Spark means unlocking the true potential of data in today's fast-paced digital world. That's all for this video. Thanks for watching. I'll see you in next one.